Let's draw more Lewis structures. Try these. So nitrogen with 5 valence electrons. It's in the 5th column of the periodic table, and 3 for each hydrogen for 8 total. So we would put the nitrogen in the middle, attach 3 hydrogens, and complete the 8 total electrons with an unshared pair. You absolutely could draw that unshared pair as dots or lines. Continuing on to the ammonium, this of course is ammonia, and this is ammonium ion. And with 8 valence electrons again, the nitrogen in the middle, and this time 4 hydrogens attached. And it's common practice to put polyatomic ions in square brackets and indicate the charge outside of the brackets. Lastly, carbon dioxide, 4 valence electrons on carbon, 6 on each of 2 oxygens for a total of 16. Put carbon in the middle, attach an oxygen on each side. That's used up 2, 3, 4, 5, 6, 7, 8. And we find out that we don't have enough electrons. You may, of course, have put your electron pair on the carbon. Doesn't matter. Either way, we can find out that we don't have enough octet. We don't have an octet around each of 2 atoms, and so that indicates that we'll need some double bonds. So we'll move 1 to give the oxygen on the outside an octet as well as the carbon, but you'll need another one in order to complete the octet with this oxygen. You may have done a triple bond on the carbon, and carbon to the oxygen. However, if you have done that, you would notice that you would have formal charge. And so if we check the formal charge, which you never have to do for AP unless they ask you explicitly. So if by chance you were asked for a Lewis structure of carbon dioxide, they would actually accept either one. I would hope that you would know it would be this one, because the formal charge on the right-hand structure leads to a formal charge of -1 on the oxygen and on the left, and a +1 of the oxygen on the right, because oxygen has 6 valence electrons, -6 because of the 3 unshared pairs, -1 because of the bond, equal to -1, and the carbon on this side, 6 valence electrons in oxygen in the periodic table, -2 because of the unshared pair, and -1 each for the 3 bonds, so -3 would give us a value of +1. So this would be the preferred structure for carbon dioxide. Try these 3. So we see that boron is located in the 3rd column of the periodic table, giving it 3 valence electrons, fluorine in the 7th column, 7 each, for a total of 24. We'll put the boron in the middle, arrange the 3 fluorines around it, and complete all the octets around the fluorine. And when we do that, we find out that boron comes up short. It's tempting to think, okay, we should redraw this with boron in the middle and the 3 fluorines around the outside, and instead, when you locate your unshared pairs, instead take one of the unshared pairs and turn it into a double bond. That is not necessary. No need to make expanded octet unless necessary, as you will find out in the next 2 structures. So this is actually acceptable. Boron has less than an octet. This is the only element that you will find on an AP exam that you may see this happen. So then for phosphorus pentafluoride, we have no choice but to put the phosphorus in the middle with the fluorines, 5 fluorines surrounding it. and adding all the unshared pairs around each fluorine to complete the octets. That will add up to 40 electrons, and this, of course, is called an expanded octet, and is fully acceptable. And certainly what we should pay attention to is that this expanded octet will only occur with elements in the third period of the periodic table and beyond. You will not find expanded octets in the second, or certainly you won't find any central atoms with expanded octets in the first or second columns of the periodic table. And so the last one, sulfur hexafluoride, sulfur in the middle. Let's put our 6 fluorines around the outside. And it's easily, we can complete all of the octets on each of the fluorines. Will round out and give us 48 valence electrons for this molecule. Again, an expanded octet. 4 more Lewis structures to try. First, sulfur dioxide with 18 valence electrons, sulfur and oxygen both containing 6. We'll put the sulfur in the middle and the 2 oxygens around it. That accounts for 2 lines, and we need 9 total. 2, 3, 4, 5, 6, 7, 8, 9. Again, it doesn't matter whether this line is here or here. Either way, you'll find out that one of your atoms is going to come up with less than an octet. That means we'll need to erase one of these lines and put it in as a double bond. Now this, of course, is a resonance structure, and so you could redraw this structure with the double bond on the opposite side. Either one is acceptable, and if you were asked something about bond length or asked explicitly to draw a resonance structure, you would want to do this. Carbon dioxide with its 16 valence electrons, 4 on the carbon. Carbon's found in the 4th column of the periodic table, 6 on each oxygen. We'll put carbon in the middle, which is very typical, and we'll end up with 3, 4, 5, 6, 7, 8, maybe something like this for all of your electrons, and you can see that the oxygen on either side. You may, of course, have put your extra electron pair outside on one of the oxygens. It doesn't matter either way. We have 2 elements, or 2 atoms, that don't have an octet. Our central carbon now does not, and one of the oxygens does not. So we'll need to make some double bonds. We'll erase this and put it in the middle, in between the carbon and the oxygen. Now our oxygen on the outside has an octet, but our carbon in the middle does, but the oxygen on the left side does not have an octet yet. So we'll erase one of our unshared pairs on the carbon, place it in between, and we'll end up with an octet around each of the atoms, 2 double bonds. You may have thought, well, why not draw a triple bond? And certainly you could do that if there was no other information on the question. Either one would be allowed by AP because in fact we've completed the octet for all the elements. However, we do end up with formal charge on the oxygen. This oxygen on the left will have, of course, all oxygens have 6 valence electrons, -2 for the unshared pair, -3 for the bonds, and so we'll end up with a +1 formal charge. And the carbon on this side, the oxygen on this side, 6 valence electrons, -2, 4, 6, and then -1 more for the bond for a value of -1. And so because we see formal charge here, this will be our preferred structure with formal charge of all zeros. Next on the page, our carbonate ion. And so we see 24 electrons. We'll put a carbon in the middle and put 3 oxygens around it and finish the octets. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that looks great, but if you look carefully, you'll notice that our carbon in the middle does not have an octet. We'll need to erase one of them from one of the oxygens and put a double bond, which will then give us an octet around each of the atoms. Seeing that it's an ion, it would be best if we put it in square brackets and show the charge outside. Now you can see I drew the double bond there. The double bond could equally be here, or the double bond could be over here. So if the question asked you explicitly to draw resonance structures, or you were asked something about length of bonds, you would want to draw two other resonance structures, connecting them with double arrows. Lastly, we have nitrogen monoxide, which is interesting because of its odd number of electrons. This is called a free radical. Odd number of electrons is a free radical. And so, let's take a look. We want fewer electrons on an atom, not more, and this is because there's not any set of valence orbitals able to hold more than 8 electrons. Unless, of course, we're expanding an octet, and that can't happen with nitrogen and oxygen. So NO with 11 electrons, NO2 with 17 electrons. You'll see, let's try one of them. NO, put them together. That's 2, 4, 6, 8, 10, and then we've got one more electron to distribute. However, we will not end up with either atom with an octet. So let's erase one of these and put a double bond in between. Now I've used 10 electrons with an octet on the oxygen, and we'll park the extra odd electron on the nitrogen so that it is, you see, coming up short. We always want to end up with fewer electrons on an atom, not more, and the less electronegative atom, which is nitrogen in this case, will end up with less electrons. As you can see here, the nitrogen ends up short without the octet, and again here the nitrogen is ending up short without the octet.